Okay, and we are in create function. You can see that it's implementation of EVM interface or struct. And this is really similar between create and create2. In both cases, we are calling evm.create. What is being different is contract address, because in contract 2, as you can see here, we have ff concatenated with message sender and salt and catch-up of init code, and we take last 20 bytes of it, like in case of every account. Okay, so let's see how evm.create is being implemented. Here we are using a tracker, and we check if the depth, which is 1024, is exceeded. If it is, we are throwing an error. Also, we check if we can transfer. You can see that what we have is not direct function implementation, but a reference to function. This very similar concept is also in Solidity, where you also have function selectors that you can pass around. So this is done here, and this is done mostly because depending on EIP that is being active on specific block, the rules may change, and we will see that later when we will go into paying for the gas. Okay, so if we search through references of it, we are landing here how new EVM is being initialized, and we see here function get transfer, which checks if balance of the address is at least of this amount. Similar, a transfer function is just really simple subtraction of balance in case of sender and adding it in case of recipient. Next, we have check for nonce overflow, and we update nonce here. So that's the difference. If you are having a call operation, you are setting nonce before, but when you create, you set nonce here inside. And this is done because when you deploy contract, you are increasing nonce of the caller. It is both for externally owned accounts and for contracts. You probably already heard about it, maybe even I told about it in some of the previous episodes, that smart contracts change nonce only when they deploy an address, and in case of go-ethereum, this is implemented here. In current block, at least changes from Berlin hard fork are active. You are adding address to access list. Access list is actually warm access list, so if you are using either address or storage slot for the first time, you are paying more, and every other call to the same address or storage slot costs less. And this was introduced in Berlin. Hard fork, and you will see many of such conditional statements here, because go-ethereum has to work with all the hard forks that are being introduced ever in EVM, and it has to do it progressively. So each time that new EIP is being introduced, it also has to work on the code that was introduced before the hard fork. So that means that you have to contain all of the legacy code that is there. Next, we get code hash just to see if nothing is being deployed on this address. So we cannot deploy twice on the same address. So we check if get nonce is not 0 and contract hash is not default value and it's not empty code hash. If it is, we throw an error, error contract address collision. And here we have snapshot, and this is interesting part. If we go into implementation of snapshot function, it returns an integer. And what it really does is just increasing revision ID and adds this revision here. So this is an important topic that I want to tackle here. So how go-ethereum implements the possibility of revert. As you know, if something unexpected or sometimes expected happen, but if execution is reverted for whatever reason, you need to revert everything in current call context up to the level where this revert is not being bubbled up. So for example, if you have some low level call and you check return and false is being returned to you, that means that it reverted. So you can either decide to revert it. In this case, your current call context will be reverted as well. If you do not decide to revert in this case, only the function inside and all the possible call context that it had, all the possible hops through different contracts that it made, only those will be reverted. And how, you know, how go-ethereum knows that they have to revert only like this specific code changes and not the others. go-ethereum uses journal. For that journal, you can think of it as a simple array. So let's say that we start with 0 or 1. This is our initial state. And each time with each new context, with each new call context, and create is also a new call context. Because as you remember, when we are executing constructor, this is really another call, and we will see that here, that create, what it really does, it inside uses normal call, just as if you were to call any other contract. What go-ethereum does, it each time that you call snapshot function, it increases the counter that it has, and then all the changes that you make. For example, if you are changing balances of users, if you are emitting an event, changing some storage slot, whatever you do that changes the underlying database, it is being appended as journal entry. And journal entry also has information, what is current state, what is state that was there before. And journal entry always has this information about previous state. So this is super useful, because then if you are reverting to snapshot, then you are going backwards from the last element in this journal entry, and then you know in which snapshot it was done, and you know to which revision you have to revert it, and all the changes, because remember, journal has a previous state. So each time you are just applying the previous state, so you are undoing the changes that were made up to the revision ID that you want. And this is how go-ethereum makes sure that everything is reverted. And if you think about it, what could happen if you didn't revert it correctly? Well, many bad things, but maybe you could send some money to someone else. Let's say you have $10, you send it to someone, you revert it, but the change is not being undone. So still, even though you, for example, have the same amount of dollars as you had before, you know, the account that you send it to also has this money. So you have infinite money glitch. And I think that one of the chains, custom chains, had issue with that. I can't recall right now if it was EVM based or not, but I do recall reading an article about one of the chains that had reverts, but reverts didn't really work. Fortunately, it was found by White Hat, and the risks were mitigated. However, it could be dramatic in consequences if it was found by some black hat. Okay, and quickly about the journal that I told you. As I said, you are adding journal entry. There is multiple types of journal entries that might be. You can see here that you have, for example, journal for refund change, adding log, pre-image, touching some contract, which means warming it, transient storage, and you have for each of them, you have revert and dirtied. The dirties are required when we are finalizing the state, and we can read here what it really does. Finalizes the state by removing the destructed objects and clears the journal as well as refunds. Finalize, however, will not push any updates into trees just yet. Only intermediate root or commit will do that. So the finalize is a prerequisite to committing state. So you are gathering the journals during execution. You are gathering what contracts have to be deleted, because contracts are not, if you are calling self-destruct, it's not being removed until the end of transaction. And also you are checking the refunds that have to be done after transaction. And here you are just going through everything, applying it to the new state that will be saved to the database. And you can see here that we are going through all those dirties. That's why we have to add them, and we verify if this is being self-destructed or it is being empty, and remove all the possible intermediate changes to be prepared for new execution. I mean, execution of a new transaction. And you can see, for example, here that self-destruct change has 3 parameters. First is account that was being removed. Prev, it means that if the account was already self-destructed, because remember, it is only being removed after transaction ends, so you can call multiple self-destructs, and actually all the other self-destructs will be a no-op, nothing will happen. And the previous balance, because balance is being zeroed out in this case. So what revert does, it takes this journal and it just takes, previous value of self-destructed and sets the balance that was added to the journal. So we may have multiple kinds of journals, as you saw, one for changing balances, one for self-destruct, yada, yada, yada. Again, as I already told you, we are going through entries and we are starting with length of entries -1. So we are starting from the end and we are applying all the journal entries by calling the specific revert on it. Okay, so we can see here that we return snapshot, and if anything happens, error is not null, and this is at least homestead, and the code is different than out of gas, then we are reverting to the snapshot that we made. So all the changes that were done inside are being reverted to the state from here. So before creating account, transferring and everything. And why we are not reverting when this is out of gas? This is protection against denial of service attacks. Again, imagine situation when some attacker creates a function that will not have enough gas. It is tried to be processed and it reverts, and together with that, the user balances revert. So that means that he can perform this attack for free because all his balance updates from burning the gas are being reverted. So this is protection against that. And important stuff, if this is the error is any other run execution reverted, So execution reverted is when a revert is being thrown. For example, if you throw it yourself or the contract that you are calling is reverting, in this case, we consider it as normal revert and we do nothing more. However, if this is any other error, for example, if we are accessing the stack element that doesn't exist or any action that is not allowed in EVM, we will use all the gas. Yeah, you can see all the gas that we have left, we are using it. So this actually is how assert, for example, works, because assert, as you remember, in previous version used invalid opcode. And invalid opcode is on go-ethereum case, it's just an operation that, returns an error, and the error is not the same as revert. So in this case, all the gas is being burned. Again, this was in Solidity 0.7. Now assert works really similar to revert because it does not burn all the gas. Okay, after creating a snapshot, we are creating account in StateDB. And if this is EIP 158, we are setting nonce to 1. So remember, if the contract is being created, it has nonce of 1. And then the nonce for contract only grows if this contract deploys any other contract. Okay, and before anything is being run, we are transferring from the caller to the address that we are just creating. So this is in the case that you have payable constructor and you are sending some value together with the create. Next, we create new contract. We have information about parent, how much gas and value we have. And also we have jump desks. There is like jump desk analysis, which just means where the jump destinations are. And if you are trying to land on any other opcode that is not jump desk, it will revert on you. Next and finally, we are running the interpreter. So here we are executing our init code. The init code, this is actually the constructor. So here we are running the constructor, and constructor has to return the code that is being returned. And we will go into run a bit later, but you can see here that we are using the contract input, which in this case is nil, just because in contract creation, the contract code itself is used and the contract is call data itself. So just in case of create, how go-ethereum treats that is that only the contract code, that the code that we set here is being used. And if this is read-only is only set to true if we are using static call. And that's how the processor knows when to revert when you are trying to modify some state while you are into like view function, for example, where you shouldn't change anything. Again, the code to be deployed that is being returned by this interpreter is checked if it does not exceed the maximum code size. If this is at least London, and that means that EIP 3541 is enabled, we are also checking if first byte is EF. This considers additional format notation because this EIP just reserves these 2 bytes, but in the future, when another EIP is being active, it will, after it, there will be a version of Solidity or EVM, I'm not sure, that it will be running on. It would be very useful because you can see here that depending on the chain rules You have, constantly you are switching how the code is being treated, and how the transaction is being treated. And this is because all the code, whether it is being deployed in Solidity 0.4 or Solidity 0.8, has to behave the same on EVM. So for example, you cannot remove self-destruct. So right now what we have, the self-destruct opcode is still there. It cannot be removed, but it just like changed what it does. Like right now, self-destruct works a bit differently. It only self-destructs the contract if the contract is being created in the same transaction. Otherwise, it just sends all the balance to the recipient that you specify. Next, additionally, we are taking the fee depending on how much code we are putting on chain, and we are using this gas. And you can see that the code is being returned here. So this is an important concept, and this is why you should not depend on code size if you want to check if, for example, this is an EOA account. You should not do that, because the interpreter.run, it executes normal code, but the code is being set here after the transaction really ends, or this current call context ends, which means that at the moment that you run the constructor, there is no code being deployed, because we do not know yet what code will be deployed there.